All right, so first step is going to be to balance it. Let's do that. We're going to need, doesn't really matter where we start. We're going to need 3 here to balance the magnesium, 2 here to balance the nitrogen, and then that should give us, let's see, how many, no, we're going to need more than that because we got 12, we've got 6 oxygen, right? So we need a 6 here. And then does that fit with the hydrogens? Yeah, 6 and 6, yep, so that should do it. If I wanted to be more careful, I would write out the numbers, for each one, which I suggest you do on the exam. Okay, so now we have a balanced equation. So let's set up our expression for calculating the water from the magnesium hydroxide. So remember, these always go the same way. Hopefully, everybody will get these kinds of questions right all the time because, or at least really close, because it's always the same expression. And so make sure when you're doing the exam that you write out the expression so that even if you miss a number or you write one number wrong or something, I'll still give you most of the points if you got everything set up properly. So we'll start with that 150 grams of magnesium hydroxide. And we want to first go to moles of magnesium hydroxide. To do that, we need a molar mass or molecular weight. So that would be, let's see, what's magnesium is 24.3 plus 17 times 2 is 34. So 24 and 34 is 58.3. Is that right? I got 58.3. That's way too big. Because magnesium is only 24. So 24 plus 16 plus 16 plus 1 plus 1. 58.3? Yeah. Yeah, 58. So there's the problem. Okay, so then we're going to do moles of magnesium hydroxide, 2 moles of water. And the equation tells us there's going to be 3 of these for 6 of these. All right, and then we've got, finally, we want to go from moles of water to grams of water. And so that's going to be 18. So let's try to calculate this out. I get 92.6. Is that right?
No. Oh, yeah, that's great.
Okay.
93.
93, okay. So that's the grams of water needed. We could say 92. All right. So that's how you do that problem. Now let's say this is on the exam and it's like a 6-point problem or something, or 5-point problem. So if you mess up the molecular weight of magnesium hydroxide because you calculate it wrong or whatever, that's still probably 5 out of 6. So make sure to write everything out, do everything else. If everything else looks good, then you can still get the correct part that you did correctly. You get counted for that.
Can you only repeat for how you calculate the 58?
Yes. So let's see, magnesium hydroxide, that's 1 magnesium, 2 oxygens, and 2 hydrogens. Yeah? So let's see, we add that up. Magnesium is 24.3.
But here they write like a magnesium 3. Down. The equation here, like Mg3. Mg3. So
No, because the 3 is in front.
I see.
Yeah, so we're not calculating this one, we're calculating this one. Yeah. All right, so there will definitely be this kind of stuff on the exam. You can count on that. Hopefully that's easy points for everybody. Don't forget your calculators. What else? I like your shirt, by the way.
Thank you.
How far back does it go? Like, how far back does it go?
All the way back.
Like beginning?
Mm-hmm.
Like the whole, like, since class started?
Yep. Now that said, it will focus on the new things, but all the stuff we've been doing the last few chapters still requires stuff from earlier chapters. So it's not like I'm going to pick out some random fact from chapter 2 and ask you about it, but you still need to do unit conversions. You need to be able to name stuff and write down the equations from the names. So the stuff that you need to actually use from earlier chapters will be there. So technically I say it's cumulative, but that's only because we need to know some things from before to continue to do what we need to do. So the focus would be on the end of chapter 4, or I'm sorry, the end of chapter 6 that we didn't cover in the last exam, chapter 7, 8, and 9. Chapter 8 only the relationships that we talked about in class. So what happens when
So no calculation?
no calculations in chapter 8.
I have a question about lithium nitrate and lithium nitrate. So
Yes.
lithium nitrate is NO2?
No, nitride is just N. So it'd be Li3N.
Only N.
Yes. Anything, well, okay, there's always exceptions, but when we look at the ion names, when they end in IDE, we're usually talking about just one atom. So nitride is N. Sulfide is S. Chloride is Cl, and so on. The exception is hydroxide, which is OH minus 1. But otherwise, that works. So phosphide, bromide, fluoride, iodide, those are all oxide, all just one atom.
Okay, nitrate, this is NO3, yeah?
Mm-hmm.
And nitrate, and nitrate. NCE.
Yeah, that's not on the list though.
We don't use.
You don't need to know that one. But it's NO2, but you don't need to know that. Yeah, there's that list of, what was it, about eight or nine
We have
polyatomic ions. Make sure you take another look at that before the exam so that you know those. The names, the symbols, or the names, the formulas, and the charges.
And about the solution, mass calculation. That's so confusing.
Okay.
Can we?
Yeah, let's do that one. That's from one of the old exams.
Yeah, no, this is for
Oh, from the
some of them.
The homework? All right, I'm just gonna do these two because that's what will be on the exam. This stuff won't be on the exam. The volume stuff.
So only this.
So mass percent and molarity. So let's take a look at that one. This is from the lab. So you've got a sodium chloride solution. .25 milliliters. Has a mass of 27.00 grams. After the water was evaporated, just like you did in lab, the mass of the solids was 4.78 grams. So we want to calculate the mass percent and the molarity. And these are the two that you should be able to do. Mass percent, that one's just going to be the mass of the solute divided by the mass of the solution. And those numbers are already given to us. Oops. So okay, that's in this case the mass of NaCl divided by the mass of the whole solution times 100%. So that's going to be 4.78 grams divided by 27.00 grams. So 17.7%. Remember, that's a percent, so that number will always be between 0 and 100. If you get some crazy big number, you probably flip the fraction, so redo that. Any percent is going to be between 0 and 100, always.
Okay, which time we will add the mass for mass of the solution?
Good question. The bottom of the fraction here is always the total mass of the solution. So that's the solvent and the solute. In this case, the whole solution has this mass. If it said that 4.78 grams of NaCl was added to 23 grams of water, then you would have to add those two together because the water and the NaCl together are the solution. If the whole mass of the solution is given, that's the whole mass of the solution. All right, so then how do we find molarity? The other one here. But, yeah. Right? Right, so this is going to be moles of NaCl per liters of solution. Now, yeah.
Find moles of
Right.
nitric chloride, yeah?
Right, so we have to solve for moles of sodium chloride. What about liters of solution? Do we have that?
Yeah, we have to do conversion.
We have to convert it. So we've got 25 milliliters. How many liters is that?
0.100.
Other way,
0.25.
like this. Because a liter is bigger than a milliliter. All right, so now to get that top part, the numerator, we need to get from grams of sodium chloride to moles of sodium chloride. So that 4.78 grams, that's the mass of sodium chloride. We can convert that to moles. By doing a grams to moles conversion. All right, so we add up. Sodium is 23, chloride is 35.5, so that's 58.5. Point 0817. And that's our number for the top of the fraction now. Which is 3.268, or we can round that somewhere, 3.3 or 3.27. So we would report that concentration as 3.27 molar NaCl.
All right, what else we got on this one?
We didn't really go through that. Yeah, that
So
was.
we need equivalent?
Yeah, we didn't do that. We skipped that section. It's not in the. No, isotonic, it has to do with the osmotic pressure. The isotonic solution is the same as the inside of the cells. So the water doesn't go in or out of the cells.
So this is using reagent mass.
Yeah, this is mass per volume, which is not something that we're going to do on the exam, but yes, so that would be 0.9 grams per 100 milliliters solution. Divided by 100 milliliters of solution. So then you convert the grams to moles and the milliliters to liters. And that's the, then you can make the molarity. I don't want to do that now because I don't want to confuse everybody because that's not on the exam, but yeah, we can talk about it.
Do we need to know about oxidized and reduced?
No.
Can we do like one example for moles, like grams to moles also?
Yep.
Yeah.
Okay.
And only moles, like we have.
Yeah, let's do one of those because we haven't done that yet. Let me save this work here. I'll type this out so we can maybe see a little bit better. I'll make this bigger so you can see it. How many moles of carbon dioxide are formed when 5 moles of butane, which is C4H10, let's see, undergo combustion? So this one doesn't give you a whole lot of information, but it should be enough to solve the problem. So butane undergoes combustion. Sorry, I couldn't make the little numbers on this one, but how many moles of carbon dioxide are formed in that reaction? So this is a big problem. You got to write down. You got to start from the beginning. Write down the whole equation, balance it, go from there. The only help you get here is that you get to start with moles instead of starting with grams, which saves you a couple steps. So give that a try, and then we'll talk about it. Is that somebody's phone from here? Is that okay? Just want to make sure. It's not balanced. Think about what kind of a reaction this is and what the products and reactants are going to be. So if you're struggling getting the equation down, I put up the unbalanced equation here. Remember, a combustion equation is always reaction with oxygen and then forming carbon dioxide and water. This is 8 and 5 is 13. This is what we have to double that. Yes, we're usually get stuck. When that happens, we get 5 and 7, which you're going to get the numbers here. So that means you have double. So we change this one to 2. So you have 2, 8, 10. And then try it. Because you're right, as you got to there.
There's a couple of them in the practice exams.
Yeah.
I don't have mine, I was not asking for her, so I can actually how to do it, so I got stuck on a couple of just like.
Yeah, so if you see that, that's usually simple, but that's the problem. That you can double. It's a common what happens. Yeah. So assume the pressure doesn't change. Okay. All right, so let's finish this one up so we can go on. This is the balanced equation. This is another one of those ones where you have to double the whole thing to get it to balance. Otherwise, the numbers don't work out. So now we can do the calculation. We don't have to do any gram to mole conversions. We just have to go from moles of butane to moles of water. And so that's 2 to 10. Oh, sorry, yeah, carbon dioxide. Thank you. 2 to 8. And that's 20. So for 5 moles of butane, 20 moles of carbon dioxide. All right, next one is this from this practice exam, so I'm just going to put it up on here. I'll just actually be working. I'll just draw it. Draw the result of the temperature change. Assume constant pressure, meaning assume the pressure stays the same. So there's a balloon or something, some kind of container with a bunch of gas in it. And it says that the temperature changes from 25 degrees C to 77 K. So we have to decide what's going to happen. Now, because we assume constant pressure, that means the pressure's not going to change. And in a problem like this, you can't really draw the pressure increasing anyway, so that would be the same. So what could be the things that would change? Either there could be more or less gas. Is that likely to happen just because of a temperature change? Probably not, because the gas isn't going out or in. So that means what property are we looking at a change in? Volume. That's the last one. So the temperature changes, and the volume is either going to get smaller or the volume is going to get greater. So we have to figure out what kind of a temperature change is this. Is this temperature going down or is this temperature going up?
Yeah.
Going down, right. It's written in a little bit of a tricky way because it's 25 degrees C to 77 K. So if you just look at the numbers, it looks like it's going up, but actually it's going down because 25 degrees C is 298 K. So let's write that. 25 degrees C is 298 K. So 298 K to 77 K is a reduction in temperature. And this is actually exactly what we did with the balloon with the liquid nitrogen. 77 K is liquid nitrogen temperature. 298 K, 25 degrees C is room temperature. So you take a room temperature balloon, you pour liquid nitrogen on it, what happens?
It becomes small.
Yeah, it becomes much, much smaller. So we can draw that. That there would still be the same amount of gas in there, but it would get quite a bit smaller. What would happen if that were a rigid container? If the container could not change shape?
That size not change?
Yeah.
Maybe it's a little broken.
Well, it could, but if that's a change in size, right? It could change pressure. So if it were rigid, it would not be constant pressure. The pressure would go down if it got colder. Like when we took that metal thing that was connected to the gauge and put it in the cold water, and the pressure went down.
But if we will like use glass material, it's a little broke or
Yeah, maybe. Maybe not. Maybe it will just get cold. So this is the kind of question that you can expect from chapter 8. Not a calculation, except for the temperatures, but the idea of what will happen when this one thing changes, what happens to something else.
And we will take something from gram to milliliter to liter to
Mhm.
do this thing. So
The conversions, yeah.
like all things, we take like similar things.
From what do you,
Exam.
oh yeah, like from the old exam? Yeah, things like that. But it will be mostly the newer stuff.
But we will not take the heat yet. We can't.
Yeah, there won't be much on the heat. I don't think I got
Like this one. Liter to
Yeah, that kind of stuff you'll need to do. But I didn't put anything in there about.
When you talk about catalyst, will speed up reaction.
That's like it's there. It lowers the activation energy of the reaction.
The problem in our lab is about rubbing alcohol volume per volume.
Yeah. The volume for volume you can calculate just like mass to mass. That's another one that won't be on the exam.
It's really.
It will not be on the exam.
Next time you said about something density here about
Mhm.
8 problem.
Right. Because if you want to convert a volume to a mass, you need density for that. But volume percent won't be on the exam.
Molten right equation.
So like we did?
Yeah, I have a question. Why we wrote the last one like that?
Yeah, good question. Okay, so a couple clues here. First, it says how many moles of carbon dioxide are formed. That says that carbon dioxide is a product on the right side. When 5 moles of butane undergo combustion. So butane undergoes combustion, means butane is in a combustion reaction. Combustion reaction is always something plus oxygen, and the products are always carbon dioxide and water. So that's how we can find that equation. This tells you the type of the reaction, and with any of the other types of reaction, we would need more information. But combustion is always oxygen, and then the products are carbon dioxide and water. So when it says combustion, we know that's the only thing it can be. What else are we going to talk about? that the ones that come out? Yeah, calculating molar mass. Yeah.
Range of this one
Mm-hmm.
to make confused
Mhm.
because first time I tried this dye.
Yeah.
Yeah.
Let's take a look at that one. So this is the last multiple choice question on the practice or the old exam. And it talks about a Lewis structure for HCN. Now, I would not ask you the question, draw the correct Lewis structure for HCN. There are some difficulties in it that you found that makes it not quite work out nicely the way that some of the other ones do. So I didn't ask that in this question. What the question says instead is which is a correct Lewis structure, right? Which is the best, which is correct, something like that. And there's some various choices. There's this one, this one, this, let me see some of those other ones if you don't mind. Thanks. And then there was the option, none of these are correct. None of these is correct. This is a pretty tough question. I don't think I would ask one this difficult this time, but let's take a look at it. So how can we evaluate which of these structures are correct? Yeah.
First, we have to know about that, how many H's, C, and none.
Right. The only electrons that can be used in a Lewis structure are the valence electrons from the atoms that make up that structure. So hydrogen has 1 valence electron, carbon has 4, and nitrogen has 5. So that's 10 total. So any structure with more or fewer than 10 electrons present can't be correct. So let's take a look at these. Remember, a bond is 2 electrons. So 2, 4, 6, 8, 10. That one's got 10. This one's got 2, 4. So that can't be right because there's a bunch of electrons missing. This one's got 2, 4, 6, 8, 10, 12. Too many electrons, so that doesn't work. And this one's got 2, 4, 6, 8, 10, 12. Too many electrons, so that doesn't work. Now, that doesn't mean that the first one is correct because there was also the option none of them are correct. So what's the other? We know these don't work because they don't have the right number of electrons. But how can we check that first one? What else has to be true in a Lewis structure? The total number of electrons, but also the electrons on each atom. So we need 8 total electrons on each atom except hydrogen, which gets 2. So let's check that. Hydrogen has 2 from this bond. Carbon has 2, 4, 6, 8. So that's okay. And nitrogen has 2, 4, 6, 8. So that's okay. So this must be a good structure. It has the correct total number of electrons and the correct number of electrons around each atom. 8 for most atoms or 2 for hydrogen.
So that is a draw thing
Mhm.
is the same. It's kind of like it's the same.
Right. But that one's got 3 oxygens. Yeah. In that case, and I think that year we did a little bit more about drawing the structures than we did this time. I wouldn't ask questions this complicated because we didn't do as much with that this time.
How about drawing like similar things, for,
Yeah, I wouldn't give you difficult ones like that to draw. We haven't really gotten into that as much.
here's a question. I should write like this.
Right. If you start with water, then you need water here and hydrogen here. Because the question is how many grams of hydrogen. And then it would be, yeah. Right. Fair.
I have wrote the concept. But it's like.
This should be moles, so that should just be one.
Well, it's here,
Right.
it's two.
Yeah, but we only use these numbers in this part.
Oh,
Otherwise, there's only one, just like that.
so this one is another.
Right. Always one.
Even they write like,
Other issues, other things you want to talk about?
I still have to.
Wait. Oh, you're doing this first? Okay, yeah. Yeah.
the equations. Here's 4, 3, 4.
H2 is not 2.2. It's 2.02.
0.02.
And H2O is not 18.2, it's 18.0 or 18.02. So it should be this one, I think, but yeah, you'll be closer if you use those other numbers. You can just round those masses.
Okay. The H's will be 1.01.
Yeah.
Then multiply 2, and O's will be 16.
Yeah. Do you feel confident about this one? Yeah, most of the stuff. Yeah. All right, so let's review it. An isotonic solution, nothing changes. The solution has the same concentration as inside the cells. So then what happens with a hypertonic solution? Well, don't look at it. What does it mean to be hypertonic?
A lot of water.
No, less water, more stuff.
Yeah.
Hypertonic means more ions. Tonic is like ionic. So tonic, ionic. So hypertonic means more ions. If you have more ions, that means the concentration of ions is higher. So the water, which way does the water go? Out of the cells, yeah. And then hypotonic is the opposite. There's a picture in the book, or a problem in the book that is good with this too, to help think about this. I think it's down here somewhere. Yeah, something like this. A semi-permeable membrane separates two compartments A and B, and then so there's some like different things that happen, and you decide which one is which. All right. So let's say the first row, A. Solution in A is 2% starch. Solution in B is 8% starch. What happens? If they start level, which one gets bigger? Which one gets higher? And which one gets lower? Or do they just stay the same? Well, so like if we start even, which one would it be after we let it sit for a while? 1, 2, or 3? 2. Because the lower 2%, here, higher 8%, the water would go from here to here to try to make them equal. The water goes from lower concentration to higher concentration. So that means that the water would get pushed into B, and that would make number 2 correct, or number 2 the final thing. All right, what about B? If they start at 1% each.
So it's the same.
Yeah, stays the same. Right. And then what about C?
It is 3.
Yep,
from 1 to 3.
right. And then D,
It's 2 from 1 to
0.1 to 1, right?
so
Okay. So A,
Yeah,
the number 1 will be A there. Yeah? No.
no, it
Number
says,
B.
if you have, no, it's the wrong way. This is the question, these are the choices. So if we have this situation,
So we-
which one will we have? We will have 2. Because this will push over to this one. So interesting, is there any difference between the starch and the sucrose? Why is that different here? You know, what's the difference between starch and sucrose in terms of these membranes?
starch can't pass
Right.
the permeable.
Starch is too big, it's a colloid, and it can't go through the membrane, but sucrose can.
Sugar. Sucrose.
Yes, right, sugar. So that can. So in this case, I mean, that doesn't change the question really, but in a real situation, you would not change the amount of starch on either side, but eventually you would actually change the amount of sucrose. So the sucrose and the water would both move, and eventually I think it would probably even out after a while, after long enough. In fact, let's check that 977. Does it, I wonder if it would say that. Yeah, no, it says that there either, but I think the book answers the way that we answer. But if we think about it, if the sucrose can go through the membrane, if we let enough time pass, it should end up at 1, right? The glucose would actually move, and the water would move, and everything would end up even again after a long time. But initially, the sucrose ones would be the way that we said. So I don't know. You have to do the experiment and see.
So A and B thing is using kind of like a osmotic pressure.
Osmotic pressure, yeah.
Osmotic pressure.
The osmotic pressure is the pressure on the membrane that pushes the water up as it transfers. Well, no, I think the way the question is asked, I think it's still osmosis from the movement of water, but there will also be some dialysis there. The sucrose will move also.
So we should know the name for the low
Yeah, hypotonic, hypertonic, isotonic. You should know those words.
How about 21? This is something we did here with 150 grams, yeah?
Yeah.
We were looking.
Yeah.
Yeah.
That kind of thing, yeah.
I'm not sure about balancing, but we have to double.
Mhm.
Can't understand this.
Well, there's different tricks. That one's a good example. Let me pull that up, 'cause that's a hard one to balance also. This is another one from the practice exam. Okay. So this is another equation that's difficult to balance. And one of the things that makes it difficult is that the different atoms are present in different molecules on the same side. So remember that rule that we always leave for last those atoms that are in multiple different molecules. In this case, oxygen is in everything, so we're definitely going to leave that to last. But also nitrogen is in two different things on the right side. So we don't want to balance that first because it's going to throw us off. Anytime an atom is present in multiple molecules on the same side, you want to leave it till last. So that means that the only way to really do this is to start with hydrogen. Because that one is the only one that's really clear. We've got 2 on the left, 1 on the right. So if we put a 2 here, we will have the hydrogens balanced. Now we'll go to nitrogen. We've got 4 on the right, or I'm sorry, 3 on the right and 1 on the left. So we should put a 3 here. And then the oxygen just works out, right? 7 on the left, 7 on the right. We don't have to do anything about that. Now, if you had started with, let me show you. If you had started with nitrogen or oxygen, it wouldn't work. So watch this. Let's start with nitrogen because it seems like the first one seems, okay, yeah, we start with nitrogen. 2 on the right, 1 on the left. So we put a 2 here. All right, then we try to balance the hydrogens. Or then we try to balance the oxygens, let's say. We've got 5 on the left, 4 on the right. You know, it's going to be hard to balance, so maybe we put 2 here, so we have 5 on the left and 5 on the right. But now the nitrogens don't balance anymore. So now we go back to the first one, and we change this one from a 2 to a 3. Okay, but now all we're thinking about is nitrogen and oxygen, nitrogen and oxygen. So now we've got 7 on the left and 5 on the right. So then we change, I don't know, maybe we think about changing this one to a 4. So we have 7 and 7, but now the nitrogen doesn't work again. And it will keep going forever. It will never work. And the reason it never works is because that nitrogen and oxygen are in multiple different molecules. And so when we decide to balance by only changing one, even though there's 2, we don't know if we picked the right one to change. So you always want to save until last the one that is in multiple different molecules. So that's one trick, that to make sure that you do that. And if you see this, if you see the situation where, okay, I changed this side, now I have to go back and change this side, now I have to go back and change this side, now I have to go back and change this side, and it's just going up and up and up and up forever, this is maybe one reason. Another reason is maybe you wrote the formulas wrong. Because that shouldn't happen. It shouldn't keep going up and up forever. It's not like once you get high enough, it will magically work. It will never work if it keeps doing that. So go back to the beginning. Think about starting in a different way. Try a different atom first is a trick there. Now, in certain situations, the doubling situation is when you have an odd number of something on one side, but you can only change things in multiples of 2 on the other side. Then you know the whole thing needs to be doubled so that you can do it in multiples of 2, which is what we saw in that example earlier.
Can you show some equation when we double?
Yeah. Let's look at another one. So this happens a lot with the hydrocarbons, the combustion reactions, because of the ratios that come up there. I'm trying to think if I can think of a different one, but I don't think I can think of it off the top of my head. So let's try this one. Here's another combustion reaction. So again, it doesn't matter which atom we start with, but we have to leave oxygen until the end because oxygen is in 2 different things on the right side. So we can start with carbon, we can start with hydrogen, but we cannot start with oxygen. All right, so let's start with carbon. We've got 8 on the left, So we put 8 here to get 8 on the right. Then with hydrogen, we have 18 on the left. So we put 9 here to get 18 on the right. And now we do look at the oxygen. On the right, we have 16 plus 9, which is 25. But there's nothing we can put next to that O2 to make 25 because it has to be an even number. So if we put, well, we can try it. If we put 12 here, that gives us 24. That's not right. If we put 13 here, that gives us 26. That's not right either. So when you get to that situation, that's how you know the whole thing has to be doubled. So we're going to put a 2 here. And then instead of 8, we'll put 16. And instead of 9, we'll put 18. Now if we add up all those oxygens, we've got 32 plus 18, which is 50. And 50 divided by 2 is 25. So now we can get it to work. All right. All right, we are about out of time. So if you got more questions, you can ask me or upstairs, or I'll see you tomorrow. I will be here a little early tomorrow, so if you have some last minute questions, come by my office before the exam. I'll be there. Yeah.
This answer.